Hi students, good evening. Welcome to this video session. I remain Samuel Dominic Chukwu Emeka, aka Sam Dom for Peace, as usual. In this video session, we shall discuss Modular Exponentiation Part 3. So, if you go to this website, www.modular-arithmetic.appspot.com, www.modular-arithmetic.appspot.com, you will see we discussed, if you go to the videos now, you will see it's two methods. The first method was modular exponentiation using modular exponentiation algorithm. So we discussed that already. The second method is modular exponentiation using the method of repeated squaring. Okay? So those two methods are the most important methods that you should know, okay, as a computer scientist, as a mathematician. You should know those two methods. If you're in computer science, then it's very important that you know the algorithm, modular exponentiation algorithm. However, it does not hurt if you know other methods. Okay, the one we are going to discuss tonight is very easy, but it has some conditions. Okay, it is the Fermat's little theorem. Okay, that's what we are going to discuss tonight. This is a modular exponentiation part 3. Modular exponentiation part 3. Part 3. And that is the Fermat. I'm going to call it, let me write the whole name. Pierre de Fermat. Fermat's little theorem. Little theorem. So Pierre de Fermat, of course, maybe you have heard of him in your previous courses, or maybe you've not, but he's a French mathematician, Pierre de Fermat. I hope the French folks, I am not sure I pronounced his name right. I should. Okay. Pierre de Fermat. Okay. So this mathematician, he has another method to solve modular exponentiation problems. However, his method does not solve all modular exponentiation problems. So, accordingly, I am supposed to teach you those examples I did. The examples I did using the two methods. Okay, the modular exponentiation algorithm, that's the first method, and then the method of repeated squaring. Okay, fast modular multiplication. So I'm supposed to teach you with the same examples. However, I cannot. Okay, so I'm going to do a totally different examples here. So if you have viewed the videos, if you view the part 1 and part 2 of modular exponentiation video, don't be surprised if you now see different examples here in this video. Okay, because those two examples will not apply in this video. It will not apply. So, but however, we're going to discuss the examples that would apply here. And for those examples, this method is better, much more better. Okay, the only problem is that it cannot solve all modular exponentiation problems. Okay, so what is this theorem? This theorem states that if you have, say you have, okay, an integer, I'm gonna call it a, an integer a, okay, and a prime number p. So say you have an integer a and a prime number p, okay, such that the integer is not divisible by the prime number, okay, such that the integer is not divisible by the prime number. So what do I mean by this? Such that p cannot divide a, okay? So p cannot divide a. P does not divide a. Okay, remember, if it's p divides a, it's p divides a. But here, p does not divide a. So a is not divisible by p. Okay? You have an integer a and a prime number p such that a is not divisible by p. So p does not, in other words, p does not divide a. Okay? Prime number does not divide a. Okay? The prime number does not divide the integer. The prime number does not divide the integer. What I mean by it does not divide it without a remainder. That is what I mean. Okay? Does not divide the integer without a remainder. Without a remainder. That is what I mean by that. So if you have something like this, okay, then number one, Pierre de Fermat found out that a exponent p is congruent to a in mode p. A exponent p is congruent to a in mode p. So which means that p will divide a to the p minus a. That's, in other words, p divides a to the p minus a. That is the first thing, okay? P will divide a to the p minus a. That is what modulo means, okay? By now, I expect you, if you go to this website, if you click on videos, it is good you follow those videos in order, okay? So, I expect that you now know this, okay? Then number two, a to p minus 1. A exponent p minus 1 is congruent to 1 in mod p. So, what does this mean? In other words, P will divide, P is going to divide a to the p minus 1 minus 1. A to exponent p minus 1 minus 1. So that is what this theorem is saying. This is what this theorem is saying. Anytime you have an integer a prime number p, okay, such that a is not divisible by p, then a to the p is congruent to a in mod p, okay, and then a to exponent p minus 1 is congruent to 1 in mod p. Okay, quick example of what I mean. If we have something like, let's use simple numbers. Okay, let's use simple numbers. Let's say 2 exponent 3 mod 3. Okay? Okay, in this case our a is 2. In this case our a is 2 and our p is 3. So we have 3 is a prime number, 2 is an integer, and 2 is not divisible by 3 without a remainder. So 3 cannot divide 2 without a remainder. Okay? So what this guy is saying, what Fermat is saying is that 2 exponent 3 is congruent to 2 in mod 3. What does it mean? 2 exponent 3 is 8. So 8 is congruent to 2 in mod 3. Okay? Which means that 3 can divide 8 minus 2. Okay, 8 minus 2 is 6. So 3 will divide 6. Okay? So 3 can divide 8 minus 2. That's it. 3 can divide that. It is also saying, he is also saying that 2 exponent 3 minus 1, okay, is congruent to 1 in mod 3. So this is 3 minus 1 is 2. So 2 squared is congruent to 1 in mod 3. So this, he's saying that 3 will divide, so this is 4 is congruent to 1 in mod 3. So he is saying that 3 will divide 4 minus 1. That is what he's saying. These two. That is going to divide that. Okay? So this is the two important theorems. The two important statements in his theorem. I'm going to give you a third one now. I'm going to give you a third one. Use this theorem, okay, and I'm going to write the third one here now. The third one, okay, number 3. Use this theorem if you're given, so you will notice here, you're going to notice here that for you to use this theorem, it has to satisfy these conditions. That P must be a prime number and that A is an integer not divisible by P. So P cannot divide A. Okay, so you see this is the conditions. This is the condition. This is the condition here. The conditions. So you see why that is part of the reason why we are not going to use, that is part of the reason why we will not use the examples we've used in the previous 2 videos. Okay. Now, the next thing that you should know is this. If you are now asked to find, okay, let's say you now want to find a to the k mod p. Okay? Make sure after you have satisfied these conditions, if you are asked to find, because you're going to use this to do calculation, make sure that K is greater than P. Okay, just make sure that it's greater than P. Make sure that what you're going to use it for, that your K is greater than P. Make sure. If it is not great, if you want to try it, you can try it. If it is not greater than P, then before you solve it, you're gonna do several steps. You're gonna do several work before you solve it. Okay? It's not that you cannot solve it, but you know, there are more things you will do. So, for you to use this theorem, make sure number one, the condition, it has to be a prime number P. Two condition, the prime number will not divide the integer. The third condition, what you are now asked to find another integer. Okay, K is also an integer. K is an exponent. Okay, is an integer. That's the exponent in this case. The exponent. If you're not asked to find this, make sure that K is greater than P. So if you look at the examples we did in the previous two videos on modular exponentiation, the K was less than the modulo. Okay? K has to be greater than the modulo. K has to be greater than the modulo. K has to be greater than modulo. The ones we did in the previous examples, in the previous two videos, the exponent was greater than the modulo. Was less than the modulo. The exponent was less than the modulo. Okay, in those previous two videos. But in this one, the exponent has to be greater than the modulo. Exponent has to be greater than the modulo. Okay? Exponent should be greater than the modulo. Now, let's solve questions. Okay? Let's solve problems right away. So I'm going to do maybe two examples, and that would help. Okay? Now, if it's good to practice. Practice makes perfect. In this website, I'm going to now move those things to solve the examples. Okay? I will still introduce the topic, modular exponentiation, and the calculator on the main page. However, if you now want to see the more examples, then you have to go under solve the examples to see more examples of these. Okay, we have part 4, another method. Watch out for that method. Okay, watch out for that method. But hey, for this method, I love this theorem. Trust me. Provided it meets those conditions, that's what I'll use. Now, if your professor insists on a specific method, then you use the method your professor wants you to use. If not, if it meets these conditions, go for it. Alright, let's look at example 1. Let's find 3 exponent 302 mod 5. 3 exponent 302 mod 5. Okay, let's solve this. So, of course, you're not going to do 3 exponent 302 in your calculator. That's a long number. Okay, so first of all, let's verify the conditions. We have to verify it. We have to. Okay, so here P is 5. So we see that P is 5 and A is 3. Okay, is 5 a prime number? Yes, it is. Can 5 divide 3? No. Can 5 divide 3 without a remainder? No. So So these are the two things you have to note. Okay? Forget about this exponent first. Forget about this. We're looking at 3 and 5. The p is 5 and the integer is 3. So the first thing you ask yourself is 5 a prime number? Yes, it is. Can 5 divide 3? Because the integer now is 3. The base. Okay? A is the base. I think I called it integer. You can also call it base as well. Okay, call it base. Okay? A is the base here. You can call it base. It's the integer. In this case, base. Okay? So, is 5 a prime number? Yes. Can 5 divide the base, the 3? No, it cannot. Therefore, this will work. Then, these are the two conditions, okay? Now, the third one, remember I said the third one. The third one, look at the exponent. The exponent is greater than 5. Has to be, okay? So, 302 is greater than 5. The exponent has to be greater than the modulo. Then you're good to go. You're good, okay? So, this works. Now, we now say, okay, we now say that 3, and I'm going to use this one. I'm going to use this number 2 because that's the main thing here. That's the main guy. So 3, 5 minus 1 is congruent to 1 in mod 5. Mod 5. That is Fermat's theorem. Fermat's theorem. This is the Fermat's theorem. Fermat's little theorem. Fermat's little theorem. FLT. Okay, so this means that 3 exponent 4 is congruent to 1 in mod 5. That is what it means. That 3 exponent 4 is congruent to 1 in mod 5. So what do I do next? I'm going to leave these 2, okay, and 3. And then I'll just solve this here. So now what do I do next? I now want to look at 302. The first thing I do is, okay, let me divide 302 by 4. Okay, since I know that 3 exponent 4 is congruent to 1 in mod 5. Let me now divide 302 by 4. And let me just use the calculator. Okay, let me just use the calculator here to save time. 302 divided by 4 gives me 75.5. So 302 is equal to 4 times 75 plus, now that 0.5 times 4 gives me 2. Okay? Gives me 2 plus 2. Okay? 302, you divide, because this 302, just divide it by 4 because we want to simplify everything. So 302 is 4 times 75, remaining 0.5 times 4, okay, remaining 2. So if you want to verify it, 4 times 75 is 300, plus 2 is 302. So this means that 3 exponent 302 mod 5 will give us 3 exponent 4 times 75 plus 2 in mod 5. In mod 5. See that? So this means 3 exponent 4 times 75, law of exponents. Law of exponents. Times 3 exponent 2 in mod 5. See that? That is what this is what it means. Because this is law of exponents. Okay, law of exponents. This plus, if you, law of exponents, this means 3, 4 times 75 plus 2, from law of exponents. And if you don't understand what I just did, you gotta go to algebra. Okay, you go to my website, Exponents and Logarithms. Under algebra, you look at the laws. Okay, so Now this is 3 exponent 475 mod 5 in mod 5 times, let me just put it in mod 5 like this, times 3 exponent 2 in mod 5. So this is 1. 3 exponent 4 is 1. So 3 exponent 4 is congruent to 1 in mod 5. So this means 1 exponent 75 in mod 5 times 3 squared is 9. 9 mod 5. 1 exponent 75 is not in mod 5 is 1. 1 mod 5 times 9 in mod 5. So this is equal to 1 times 9 in mod 5 is 4. 9 mod 5 is 4. Okay, at least you know that already. Okay, 9 minus 5 is 4. Okay, so this is 4. 4 in mod 5. Answer. That's the answer. So the answer to this is 3 exponent 302 mod 5 gives us 4. That's it. Period. I mean, it saves so much time. Imagine you are doing it with modular exponentiation algorithm. I mean, it saves time, right? Saves time, right? Simple. That's it. Okay. Let's do one more. Then we can call it a night. Okay. If the rest, watch out. Read the rest and solve the examples. I try to also explain them well and solve the examples, so you can review the rest of it in the solved examples. Okay. Let's do another one. Number 2. Let's find 5 exponent 2003 mod 7. 5 exponent 2003 mod 7. Okay, P is 7. Is 7 a prime number? Yes, it is. It is a prime number. A is 5, the base. Can 7 divide 5 without a remainder? No. Good. That's all. That's what you need. That is what you need. The modulo should be a prime number. And the base, the prime number should not divide the base. That's all you need. Then, the third one is the exponent greater than the modulo. Sure it is. Sure it is. 2003 is greater than 7. That's all you need. The 3 of them. That's all you need. That's all you need. And you knock it off. Okay, so we now use this here. We're going to use this here. 5 exponent 7 minus 1 is congruent to 1 in mod 7. So this means that 5 exponent 6 is congruent to 1 in mod 7. Okay? This just tells you that 7 will divide 5 exponent 6 minus 1. Okay? Alright, now, the next thing we will do is we want to break up 2003, divide it by 6. That's what we want to do. We want to now we want to do 2003 equal to what? Divide it by 6. Let's see how many, because we want to make it up to in multiples of 5 exponent 6. Okay, we want to do that so we can find the exponent of that. So 2003 divided by 6 is 333. 333 times, okay, 6 plus, okay, 333 times 6 plus. So I'm going to do 333 times 6, then subtract it from 2003, and it gives me 5. Okay, so 333 times 6 plus 5 gives me that. Okay, gives me that. All right, so we now see that 5 exponent 2003, this is in mod 7, will give us 5 exponent 6, 3333 times 5 exponent 5, all of them in mod 7. Because that is, I wanted 5 exponent 6, that is 333, I mean, yeah. Because that is what I need, it will give me 1. That is what I need here. That was actually why I divided 2003 by 6. Okay? So this gives me now 1 exponent 3333 times mod 7 times, we can now do 5 exponent 5, we just do 5 exponent 5. We can do that. It gives us 3125 times, let me use this, 3125 mod 7. So this gives me 1 in mod 7 times 3125 mod 7. You just do 3125 divided by 7, 446. Okay, then you now do 446 times 7, and then subtract it from 3125, and it gives you 3 times 3. Okay, so this is 1 in mod 7 times 3. So this is 1 times 3, and this gives us 3 in mod 7. So this now gives us equal to 3. That's it. That's it. Still in mod 7, which is 3 anyway, because 3 in mod 7 is 3. Okay? So if you want to do, this is 3 in mod 7, that's okay. Or 3125 mod 7 is 3. If you want to do this, that's fine. Or you can leave it. It doesn't matter. Okay? I'll just leave it. And that's it, folks. Is it better? Is this easier? I think so. I think it's easier. Because it means those 3 conditions, I will use it. Okay, if my professor does not specify what I should use, the method I should use, and if it meets those 3 conditions, I mean, that's what I'll use. Okay. So this is part 3. We have another method, part 4. Watch out for it. It's going to be, we're going to combine both Fermat's theorem and Chinese remainder theorem. Okay? Alright, thank you so much for listening. If you have any questions, please feel free to ask. And you have a good evening. Now, please, you can verify this. You can verify these answers using the calculators on my website. Okay? You can verify these answers. Have a good evening.